Hi guys, welcome to our first video in Chapter 25. Chapter 25 is all about nuclear chemistry. And we're going to begin by covering section 25.1, which is about nuclear radiation, something you have likely heard of before. You can see all the way over on the right our list of topics for this unit. We are going to really study nuclear chemistry, and we want to cover its application, its discovery, what is radiation, what is radioactivity, what is radioactive decay, and then we're going to also cover, of course, nuclear fission and fusion, as well as some applications. How do we produce energy with these things? And to start, you can see I've got some pictures here of what I think of when I consider nuclear chemistry. So we've got a nuclear power plant, of course, using fission to release energy. Another example of fission releasing a lot of energy in a nuclear bomb. This diagram showing some nuclear reaction, nuclear chemistry. It's labeled, and it's a really simplistic diagram of what's going on. And you can see some atom breaking into two smaller pieces. Cool. So that's nuclear chemistry. And then this meme made me laugh, right? And the picture is, of course, nuclear physics is the favorite, and nuclear chemistry is just it is neglected, right? And this is part of why it is the very last chapter in our chemistry course that we're going to study nuclear chemistry. It's because most people who study nuclear stuff are studying nuclear physics. They are worried about the energy being produced. They are worried about the implications of what's happening and like the forces that are produced in a nuclear reaction, strong and weak nuclear forces, stuff like that. Whereas for chemistry, we are really focused on matter and the types of matter that we are seeing in fission and fusion in our nuclear chemistry here. So we're in kind of a niche part of our nuclear topic here when we study nuclear chemistry. This just made me laugh because that's, of course, how it is. Like I said, it's the last chapter for a reason. So, all right, let's jump right into 25.1. So nuclear radiation. On the right, you can see pretty short objectives and vocab for this little unit here. So to start, we really want to emphasize something that is very important for us to remember, and that is that nuclear reactions are just fundamentally different from chemical reactions. I've got a table of their differences here, and we've got a schematic in the middle here where you can see like there are some major differences for a chemical reaction. The identity of our elements is going to stay the same. The atoms are going to be unchanged. They will simply rearrange. It will be the valence electrons that move around. These are relatively small energy changes. We're seeing bonds being formed or broken in this, and we can actually change the reaction rate with some familiar influences like temperature, pressure, concentration, or catalysts. But the orange dot stays the orange dot, and the white dot stays the white dot. In a nuclear reaction, it's totally different. The black dot becomes a blue dot. The identity of the atom is being changed. We are going from hydrogen to helium in the sun. That is a nuclear reaction. It's called fusion. We are going from uranium to thorium. Those are two different atoms. That happens in a nuclear reactor, right? A fission process. So they are going to become different types of atoms. We see the emission of particles or high energy rays. There are other particles. We can all have protons, neutrons, electrons, things like positrons, neutrinos, other types of particles that just don't have a role really in chemistry. And these are associated with very large energy changes. We use them in bombs and to create energy. So lots of energy change. Now, radioactivity was discovered by accident. This guy, Henry Becquerel, and I think that's how you say his name. I am not sure. Him and Marie Curie are really credited with discovering radiation. And Marie Curie, unfortunately, actually died of radiation, of cancer, due to the exposure to radiation she had while studying this. In fact, her diary is so contaminated with radiation that it has to be kept in a lead box. And if people are going to observe it, they have to take it out of the lead box, and they can only look at it so often without being exposed to radiation, like her lab notebook, that is. So very interesting stuff. But what Becquerel did, and he was really the first one to get evidence of radiation. So what he did was he was actually studying phosphorescence by taking uranium salt and putting them in sunlight. And uranium salts have this property where they will absorb sunlight and they'll go through phosphorescence, meaning that they will re-emit that light slowly over time. And it's similar to like those glow in the dark like stickers that you have. Those are also phosphorescent. So he was studying phosphorescence using this uranium salt, and he wanted to get a control. So he took his uranium salt and he put it in a drawer in his lab, and he left it there for a couple of days so that all the phosphorescence would be gone. And he even did his experiment in a dark, overcast day. While he found that he was able. So what he was doing was he'd taken his uranium salt and he would put it on photographic paper, and it would phosphoresce and it would make a mark on that paper. Well, he found that even if he kept his sample out of the sunlight, when he put it on the paper, it was still interacting with that paper. It was still making a mark on the paper, indicating there was some sort of something being released from this uranium salt. And what he didn't know, but what Marie Curie was able to actually identify, was that that rock salt was intrinsically emitting energy in the form that she called radiation. And they weren't sure what it was, but they knew that this rock would spontaneously shoot off this energy that would meaningfully interact with the photographic paper. And so this was the first real discovery of radioactivity. We now know that radioactivity is, I don't want to say common, but it's common in the universe. And there are a lot of elements that are radioactive. And so we have these things called radioisotopes. These are unstable nuclei that emit radiation in the process of gaining stability, right? Radiation is what's emitted as these radioisotopes go from being unstable to stable, right? On the periodic table, elements that only have unstable nuclei and that are not found in nature are indicated by parentheses or brackets. So you can see neptunium, not naturally found. It will spontaneously decay into other substances on its own. And we don't have any natural sources of this. Whereas our naturally occurring isotopes like uranium, those are given without brackets or parentheses. Okay. And uranium is a radioactive substance. Uranium-235 is the fuel for nuclear fission, but uranium-238 is actually considered stable and is not radioactive in the same way that uranium-235 does. It has a very, very long half-life and does not emit dangerous chemicals. So it's considered stable because its half-life is 4.5 billion years, otherwise known as the length of our solar system's life up to this point. So very stable stuff, that uranium, even though it is slowly decaying. Okay. So there are three types of radiation that we are going to concern ourselves with. There are more types of radiation that exist. These are just the most important three for us to consider. And those are alpha, beta, and gamma radiation. Alpha radiation consists of alpha particles. An alpha particle is a helium nuclei. You can actually see that over here. If we look at our alpha decay of radium into radon and a helium particle, a very important observation to note is that radium starts at a mass of 226 and an atomic number of 88. Radon has an atomic mass of 222 and an atomic number of 86. Helium has an atomic mass of 4 and an atomic number of 2. Well, if I add up the atomic numbers, 86 plus 82, I get 88, what I started with. And if I add together 222 with 4 for my atomic masses, I will get 226. Again, what I started with. So it is important that we can actually balance these nuclear reactions, and then we see that these things have, they do follow the law of conservation of mass. And I'm going to put an asterisk by that because they actually don't really follow that rule very well. So the alpha particle will, of course, have a +2 charge, given that it has 2 protons because it's a helium. Its mass is given here. Approximate energy is 5 mega electron volts, which is actually very weak. This can, in fact, be blocked by paper. So it's very weak, very little penetrative power. Your skin is another good blocker for this. Unlike the beta particle. Beta particle is actually another word for an electron. And we've seen beta particles being used before in this thing up here called a cathode ray, which is a ray of electrons. And this lead block has got a radioactive material inside of it, and it's shooting out these gamma rays. Sorry, not gamma, these beta particles. The beta particles are deflected up. So we know that they have towards the positive side of our plate. So we know that they have a positive charge. Whereas, of course, our alpha particles were deflected down towards the negative plate. So the charge of our beta particles, which again is simply an electron, right? These are indicated with a fancy B, 0 on top because they have no mass, and a -1 on the bottom because they are the opposite of a proton. So their atomic number is -1. Okay. And our alpha particle, of course, is a He for helium. But these things have a -1 charge, very small mass, and they have a 0.1 to 1 mega electron volt range of strength, which actually makes them moderately strong, and they need to be blocked by metal foil, but still not too crazy. They can be blocked by metal foil. Our third and most dangerous type of radiation is called gamma rays. Yes, the ones that made the Hulk. No, the Hulk is not scientifically accurate. I'm sorry, because gamma rays don't really mutate your cells at a rate that can be useful. They mutate them at a rate that kills you. They are very, very, very strong, 1 mega electron volt in its energy, but they are in fact able. They are not blocked by lead or even concrete. So these things are very strong. They go all over the place. They're just so small that they can fit between your DNA particles. They don't always break them. Okay. They have no charge. They have no mass. Their symbol is gamma, which it looks like a backwards Y in English. This is a Greek symbol. So we have alpha, beta, and gamma, right? The alpha particles will all often sometimes be given as the alpha symbol in Greek. Beta is the beta symbol in Greek, and gamma is gamma. So you can see gamma rays not deflected by a charged place. They have no charge. So these are our three types of radiation. And as you can imagine, a alpha particle will decrease the mass and the atomic number of our starting material. A beta particle will simply decrease the atomic number, but it will keep the atomic mass the same because there's no mass with our electron. And a gamma particle will not change the mass or atomic number of our particle, but it will change the energy. It will be an energy loss for it, which is good. Now, this brings us to two vocab words that are fairly important here. Gamma rays, which are those high energy electromagnetic radiations. They're usually very short wavelengths. The idea of a gamma ray burst is a extinction level event that could sterilize the surface of the Earth. So these can be pretty powerful. These also always accompany alpha and beta radiation, almost always. They are almost always a byproduct here of that radiation, and they are fairly dangerous. They are what makes it so dangerous. X-rays, on the other hand, they are similar to gamma rays in that they are a high energy form of radiation. They are carcinogens, but they are not actually emitted by radioactive sources. They are instead emitted by certain materials in an excited electron state, kind of like how light can be emitted. So you can see I have right here, I have an example of some beta decay. I have our alpha decay here. Here is a beta decay where a neutron is going to emit an electron. And that electron, if we take 0 and we remove a negative charge, well, we'll be left with a positive charge. So when a neutron emits an electron in beta radiation, it actually forms a proton. So it's going to increase our atomic number by 1. This iodine goes from iodine to xenon. So it increases atomic number by 1 as the atomic mass stays the same, because a proton and a neutron have the same amount of mass. So if I swap a proton for a neutron, it won't actually change the mass. And I will, of course, produce my beta particle here. Now, here is an example of some gamma radiation where our U-238 is going to form thorium-234 plus an alpha particle. Notice the conservation of mass between my atomic numbers and my atomic masses. But this is also going to accompany the emission of 2 gamma rays. Okay, so two gamma rays would be emitted, and that's how I emit that, with the gamma ray symbol. All right, guys, that's all I have for this video. Thank you for listening. I'll see you in the next one.